Hello, my name is Ariel Rokem, and that's Kendrick K. And in this video, I will describe a method that we developed called fractional ridge regression, which is a fast, interpretable reparameterization of ridge regression. And this method just came out as a paper in GigaScience. And in this video, I will describe the method, explain why we developed this method, and then we will show some code that implements this method, open source code that you can use to run ridge regression on problems that you're interested in. So the general setting of this fractional ridge regression is the general linear model setting that you see here. So in many cases in science and engineering, we want to describe certain phenomenon using this kind of set of equations. Y here are what we call the targets. Those could be measurements that you've made. They could be time series or other kinds of measurements that you've made. And then X may be what we call the design matrix, which typically refers to a set of regressors that you'd like to describe the signal, the target, as a linear combination of. And these regressors enter into the equation weighted by a set of coefficients beta that are the target of our investigation. Those are the things that we'd like to specify when we fit them all. And then there's some noise. And so a typical thing to do in this setting is to try to find values of beta. Beta hat are now estimated betas, such that the squared error is as small as possible. So here, x beta hat minus y, squared and summed. We want that to be as small as possible. And it turns out that there's a very nice closed form solution for this problem. The solution that we refer to here as the ordinary least squares solution, finding these beta hat, is specified by this set of equations that we can implement in code and solve very, very quickly. But there are potential problems. You might have situations where you have more variables, more regressors than you have data. In other situations, your regressors might be highly correlated with each other. And you might find yourself in a situation where your fit is too accurate. It's almost always a situation, there's almost always some irreducible noise that has to remain. And for example, if you have more variables than data, you can specify values of these beta coefficients such that you fit the data perfectly, depending on the values of the regressors, and have no noise left. And that's called overfitting, and we'd like to avoid that. And a classical solution to this problem is ridge regression. In ridge regression, we write out a different penalty for the regression that includes both the squared loss term here on the left, but also an additional regularization penalty. And this regularization penalty is the sum of the square of the estimated coefficients, and it enters into this error multiplied by a regularization hyperparameter called alpha. And one way to think about ridge regression is by looking at this graphical description from this book by Friedman, Tibshirani, and Hasty. And in this setting, we only look at two coefficients, beta 1 and beta 2. And let's say that the ordinary least squares solution is this beta hat up here. These contour lines in red describe the error. And here we found the solution that minimizes the squared error given the data that we're looking at. What ridge regression does is it adds to this penalty on the squared error term. It adds another penalty, this circle in blue. So the sum of the squared coefficients describes a circle in this space. And the ridge regression solution will be, depending on the value of alpha, some intersection between this, this blue circle and our contour lines of the ordinary least square error. It turns out that if you want to implement this error term, this extended regularization error term, that looks actually like this in the equations that I described before. And fortunately, that means that all you need to add to the equations that I described before is one matrix alpha I that enters into the equation here. So it turns out that ridge regression can be solved very, very efficiently, almost as efficiently as solving the ordinary least squares solution. And that makes it a very useful tool in a lot of cases where you have, for example, many, many y's for which you'd like to solve this problem, very, very large data sets that you'd like to solve this problem. It just goes very, very fast. But there's a problem. The problem is, how do you choose alpha? So I mentioned that you regularize by some meta hyperparameter called alpha. How do you choose that? And the typical current practice is to use a heuristic approach. You try a bunch of different values of alpha that cover a range of plausible values, and you select one of those values using cross-validation within your data. You choose the value of alpha that minimizes the cross-validation error instead of the squared error in the training set. And because we don't know a priori the value of alpha that we should choose, we might space it out in a log spacing over a very, very wide range of values and try those out until we find one that fits the data well. But there are other challenges. There are challenges involved in that. First of all, we really don't know what set of alphas to choose. And just because you know alpha for one target, that doesn't tell you much about the value that you should choose for any other target. So if you're doing this over multiple targets with the same design matrix again and again over multiple targets, multiple time series from a multi-channel recording, or multiple points on the map for which each one you've collected a time series, knowing alpha for one point won't necessarily tell you anything about the alpha that you should choose for any other target. So you need to repeat this for every one of your targets. And depending on the number of targets, the computational cost could be rather steep in very, very large data sets. So the solution that we propose here is called fractional ridge regression, and that is to choose values of alpha that correspond to a specific reduction in the vector length of the solution. So instead of choosing alphas out of an evenly spaced or log spaced large range of values, we'd like to specify and find the alpha that correspond to a particular reduction in the vector length of the solution. Let me demonstrate this graphically again. So in the space that I showed you before, now with these two coefficients, the length of the vector, or the vector norm of the ordinary least square solution, is the length of this vector that goes from the origin to the position of this point, the values of the beta coefficients for the ordinary least square solution. And the ridge regression solution, the norm of that solution is the length of the vector going from the origin to the position of the values that would be chosen by ridge regression given a particular level of alpha regularization. What we'd like to do is we'd like to define a new quantity that we call gamma that specifies for us or quantifies the length of the norm of the ridge regression solution relative to the norm of the ordinary least square solution. So the ratio between those. And we'd like to specify gamma rather than specifying alpha, and have our algorithm choose for us the alpha that specifies, that chooses a particular level of gamma. That has the advantage that we will span a large range of possible solutions given the data that is given to us. So just to sort of explain this a little bit more, the norm of the ridge regression solution will always be smaller than the norm of the ordinary least square solution. So gamma is a value that goes from 0 in the case where you regularize so strongly that the ridge regression solution is basically zeros, all zeros. In that case, gamma will be equal to 0. And it will go all the way to 1 in the case where the regularization is so weak that the ridge regression solution is identical to the ordinary least square solution. But it's a value between 0 and 1, a ratio. And so you can choose in that space to space out equally levels of gamma instead of choosing alphas, and then get back from our algorithm the levels of alpha that for a particular target would hit that level of regularization. This also allows you to then equate the level of regularization that you're applying across different targets. And that's because different targets will have different levels of alpha that induce the same level of gamma. So if you chose your level of gamma to be 0.5, you'd like to reduce the length of the norm of the solution to half. That would incur or induce different alphas in different targets, but the effect on the norm of the solution would be identical across those different targets, despite different alpha. Okay, Next, we'll move on to some demonstrations of these principles in some open source software. The code is all available on this website, nrdg.github.io/fracridge. And we have both Python and MATLAB implementations. And we'll show you a little demonstration of MATLAB, how to run this in MATLAB, and then another demonstration of how to run this in Python. So give this to Ken.
Yeah, I can start. I can start. That's fine. And I can just fill in some additional comments I had. So I'm going to share my screen here. Yeah, so as a whole, I mean, we didn't go through the details. I refer you to the paper to check out, exactly what is the algorithm and what is the rationale behind that. But in the end, it's providing a method. It's essentially still giving the regression solution, but really the goal here is efficiency, because the choice of the alpha range is unknown, and by reparameterizing the problem, you can control it in a very sensible way. And if you only have enough CPU time to evaluate 10 levels, well, you're guaranteed now, if you parameterize using this gamma parameter, to actually span a relevant range for each data problem. So it's really sort of a practical tool to kind of essentially use this method to control the ridge regression problem for any given data problem you might have, and be fairly confident that you're actually choosing well chosen values for the data problem. So I have here the MATLAB version of the code, and it has a bunch of documentation. So I mean, the goal is not really to read the documentation to you, but I'm just going to go over some examples that are placed in the documentation. So there's 4 examples here. They're pretty simple fake problems. I'm just going to paste them in a new window, and we'll just go through them one by one. So in the first example, sort of following the nomenclature in the slides you just saw, we're just going to generate a little toy problem. So here we have a dependent variable y, or otherwise known as target. It's 1,000 data points, and we have 10 different regressors that are trying to predict those data points. And these are all normally distributed random numbers. So it's just to demonstrate the code. And we have here actually 4 ways of solving it. This is the standard least squares solution, which should look familiar based on the slides. And so we get a set of estimates for the 10 regressors in our data problem. So it's a vector. Here we're going to actually call the code that does the fractional ridge regression. And here, for demonstration purposes, I've chosen a gamma level of exactly 0.3. So I want the kind of regularized regression solution corresponding to a gamma 0.3, meaning the solution should be 30% as long as the ordinary least squares solution. So the input syntax is fairly straightforward, and it's very fast, of course. And we actually get out the actual alpha value that corresponds to this requested fractional length, which happens to be this 2,356, of course, very inscrutable, but supposedly that is what it is, and we actually will check that in 1 second. And calling this line did deliver, as expected, a set of beta weights, so to speak. These are the linear factors on the 10 regressors, and that's put into here. So just to kind of demonstrate the correctness of the solution, we have in this line sort of the standard matrix equation for attaining the ridge regression solution, but here I'm going to reuse the supposed alpha value that achieves the regularization level I want. And so if I run that, we get some, again, a set of beta weights, 10 long. And finally, just to demonstrate the code in a slightly different way, here's a means by which you ask the code, oh, actually, I know the alpha value I want, which happens, we're just going to reuse what we got in our previous call, and you just pass in a flag to indicate that you actually intend this to be the alpha value as opposed to the fraction. And so we can also run the code in that fashion. Okay, so we just have 4 different beta estimates in a sense, and let's just confirm that everything worked as expected. So the least square solution has has maximum length, and in this case it happened to be 0.1. So this is just the sum of the squares of all the 10 beta weights, and then take the square root. So the length of that least square solution is 0.1. Let's look at the length of the ridge regression solution, which is coef2. And remember, we asked for 0.3 fractional extent. So it should be the case that this divided by this should be close to 0.3. and we do that just here. So it's very, very close to 0.3, and so that's good. And then finally, we can check some other things. So here we're just checking that our kind of standard way of computing the ridge regression solution for a known alpha value, which is coef3, should be identical or very close to identical to the alpha value, the solution we got by directly asking for 0.3 vector length. So we just subtract those two weights and just make sure it's very small. That's true. And finally, we can compare the two ways of calling FracRidge. Here we specify the fraction. Here we ask it to give me the solution for a specific alpha value. Those two solutions, 2 and 4, should be very similar. Well, 2 and 4 should be similar, sorry. The last line actually checks coef4 against 3, and that is also very small. So anyway, so this is just a simple demonstration of sort of exercising the code and confirming that the solutions are as expected. So let me speed it up a little bit. You can sort of run this on your own, but in the second example, we do some sort of benchmarkings. So I'm just going to go ahead and start running this piece of code from there to there. And if you kind of read through this, here we're just checking computational time. So we have a very straightforward, naive implementation of ridge regression, whereby we actually do some speedups. We already cache away the x transpose x part of the equation, and we're subbing in different alpha values. So this is like if you did a log-spaced set of alphas and just did sort of a naive implementation of ridge regression and just doing a for loop over every possible hyperparameter value. As you can see, it's still running, which is quite annoying when your data problems get quite big. And you can sort of think of FracRidge as not only providing you nice interpretable values, but also delivering the solutions extremely fast, because if you work through the math, it turns out the cost of one solution is about the same as the cost of as many solutions as you ask for. And we'll see that in 1 second once my laptop finishes. So just looking ahead, we're just going to benchmark the FracRidge call. So to make things comparable, here we ask for 20 hyperparameter alpha values, and here in the FracRidge approach, we also ask for 20 solutions just to make things comparable. And we can, so the previous solution took over a minute, and this new solution probably takes a few seconds, took 3 seconds. So we get obviously a huge computational speed up, given the way FracRidge is implemented at the algorithmic level. And finally, we can do another benchmark, which is one of the ways you can call FracRidge is to directly specify the alpha values, as we mentioned earlier, as opposed to the fracs. And it includes the fast way to do this, which is essentially using a single call to singular value decomposition. And you can see for yourself that they're very similar, the two different ways to call it. And so the extra cost there is to actually determine alphas corresponding to specific fractions is very minor in terms of overall computational time. Okay, so that deals with that example. And then just 2 last very simple examples. Here we set up a fake data problem, and we're just going to use FracRidge to solve it and plot some simple diagnostics. So just briefly, there are 100 data points. We have 6 predictors, and we're asking for 20 different levels of regularization. And so here's the call to FracRidge, and we get out our solutions in coef and also the alpha values, although we're not using that for the visualization. So if we take the coefficients, so let's just do a quick check of what this is. We had 6 predictors, so therefore we have 6 weights, but we have 20 versions of those 6 weights because we're asking for 20 different regularization levels. So we can simply use plot, in a sense, to visualize the contents of this coef solution. And this is very typical. This is like a trace plot where the x-axis sweeps from fully regularized to not regularized at all, and you can trace the trajectory of different parameters as you increase. As you move to the right, you're actually decreasing the regularization. So, and on the right, we quantify the vector length of each of these solutions for the 20 different regularization levels. And I guess the point of this is to confirm that this is a straight line. And if you refer to the paper, if you did a sort of heuristic log space set of alpha values and did a similar plot, this would not be a straight line, essentially pointing out that log spacing alphas is not an efficient way to space the regularizations, whereas if you use fractional ridge regression, you get a very it should be nearly straight. There are some approximations used in the algorithm, so it's not 100% straight, but it's pretty straight. That's example 3. And then finally, there is an extra mode in at least the MATLAB implementation for standardization of regressors. This is a sort of very typical regression choice. And it's important, especially for ridge regression, because the effective regularization you're imposing will depend on the scale of the regressors. And so one common practice is to z-score or standardize each of the predictors in your design matrix, or otherwise known as regressors. So in this example, we set up some fake data, fake predictors, go ahead and run fractional ridge regression. And there's a flag here too, which if you read the documentation indicates, in a sense, behind the scenes do the standardization, apply the ridge regression regularization, get the solutions, and then undo the standardization so that you can interpret the outputs in the same kind of space as your inputs. And the rest of this example just kind of demonstrates how that goes. We take our predictors x, multiply them by the putative beta weight estimates, and then add in the offset term that's implicit in the model when you use this mode. So the idea is each predictor is demeaned and divided by their standard deviation, and in doing so, FracRidge automatically adds a constant term into the model, and the weight on that constant term is known as the offset. So this model fit, I guess it'll be clearer if I just run it, what's happening. We're just visualizing the outputs. Let me just close that. So I'm showing you here the original data points that we're trying to fit in black, and we have 50 data points. And we have in these colors all the various solutions that we've obtained by calling FracRidge. In this case, we've chosen to get 10 levels of regularization from 0.1 all the way to 1, and that's getting plotted in this figure. And things sort of make sense. So if you look at Frac1, that's the least square solution. So there is no regularization. It's essentially fitting as best as it can given the constraints of the linear regression problem, and that's shown in sort of a bright color here. And you can sort of sweep your way to more and more heavy levels of regularization, and to first approximation it essentially looks like it's scaling down to a flat line, which is sort of what we expect for this kind of type of data problem. As for the standardization, what I can do is a very simple twist. So what if I simply hack out that mode and just ask fractional ridge regression to just do it on the original predictors without standardizing. So if I rerun this, we get something that looks very different, and this is not a bug, it's actually exactly what happens given this data problem. So as you will see on the y-axis, the data was deliberately put at a very high value. So the mean of the data, in a sense, is already at approximately 28.5. And by omitting the standardization, essentially that's part of the fitting. And the large differences that you can see across the regularization levels are essentially the predictors are trying to account for the mean effect. And by changing the level of regularization, that's actually the dominant effect here. Hopefully that makes some sort of sense. I guess it would have been clear. I mean, I could simply add a constant term to the predictors and then allow this regularization to take place. But anyway, I guess the larger point is that often in many regression problems you want to control the scale of your predictors, and there's a way to call FracRidge to essentially behind the scenes standardize the predictors before applying the regularization, and then essentially undo the effects of that when it returns the outputs. That's all I had for my examples. Ariel, do you want to take a stab at it?
Yeah, so I'm going to go and show some examples from the Python implementation of FracRidge. So here's I'll show you the website. So here we are in the website of the FracRidge, and we have documentation of how to install the software, how to use it both in MATLAB and in Python. On the left side here where it says example FracRidge usage, you see a few examples. I'll start with this one, coefficient paths and cross-validation curves. And if you can look here and see the code written into the page, and with some additional documentation and some figures that get generated along the way. But if you scroll all the way down, you can download a Jupyter notebook that implements this example in full. And I will start my Jupyter notebook here. Oh, I need to install Jupyter in this environment. Sorry about that. Okay. So now I should be able to open this notebook up, and then should be able to run cell by cell this example. So at the top, I just set it so that the figures get embedded into the notebook. This example will show something that's fairly similar to what Kendrick showed in the MATLAB case. We'll show some of these coefficient paths, and then show how to do cross-validation with this. I'm importing some necessary libraries. And then from the Frackridge library, I'll import a Frackridge regressor estimator. This estimator looks a lot like scikit-learn estimators. We've designed it to look a lot like estimators from the scikit-learn library, so that the API they use will be very similar to the one they use if you're using scikit-learn. And we'll also import here a few things from scikit-learn, including one of the data sets that comes with scikit-learn is this diabetes data set. It has okay, so it has one target with 442 observations, and then the design matrix is a 442 by 10 design matrix. Here are our values of alpha log spaced using the sort of the standard approach, and we use those alpha values to instantiate in every iteration here a ridge regression object with a particular alpha, fitting the intercept, and here is the fit itself. And then we store the coefficients, and we use cross-validation in order to predict and sort of evaluate how well the algorithm does. In contrast to the way that we do things with ridge regression, with the scikit-learn ridge regression, Frackridge will take a series of fractions, and much like the MATLAB implementation, it will then contain the set of coefficients and the set of alphas for every level of fractions that we've asked for. So we give it a set of fractions, we say that we'd like to fit the intercept, and then we fit just like we fit any other scikit-learn estimator. And then we predict here as well for cross-validation. Let's plot the results of this. We're going to plot down here is the coefficient plots. So here on the right are coefficient plots from the ridge regression, and here on the left are the coefficient plots for Frackridge. And what you'll see is that there's a whole set of values here at the bottom here that when you select log-spaced alphas, just have exactly the same values of the coefficients. And that's because these are levels of regularization that are they're just over-regularized. And then quickly the values change. And then again at the top here, there's a set of values for which the values of the coefficients are exactly the same. Nothing changes. And that's because those are values of alpha where things are under-regularized, or they're just not regularized at all. So what this figure should show you is that Frackridge gives you more of a dynamic range across the different values of the coefficient. Okay. In the second plot here, what we show is sort of the cross-validation R-squared of this. And again, what you'll see is on the right here are the cross-validation R-squared for the standard ridge regression. What you'll see is that it goes from very low values to very high values, and then stays at these very high values for a while. Instead, in Frackridge, things are much more gradual. We get a much larger range of different values of R-squared. In this case, R-squared doesn't differ much for Frackridge relative to the standard ridge regression. but doesn't need to be the case. We wasted a lot of computation up here on a lot of values of alpha that were just as good. I'll show you one more example. Since we're using the scikit-learn API, we can integrate the Frackridge object into scikit-learn pipelines. That, download it. Here it is. Here's the notebook. What I demonstrated here is that, let's say that you have a pipeline that involves some PCA and then followed by a regression. I'll demonstrate here how you use an object called the Frackridge regressor D object in order to do the cross-validation within a pipeline where first PCA is performed and then Frackridge is run. In this case, we generate some synthetic data. And here what we'll do is for different numbers of components in the PCA, we're going to run PCA followed by Frackridge regressor CV. This is an object that does a grid search to find the best cross-validated solution. Our scikit-learn pipeline here is specified. It has two steps, PCA and Frackridge CV. And we can call fit on the pipeline that does both of these steps. So now we're running all these different things. And then at the end, we're plotting out as a function of number of PCA components, the best fraction based on a grid search on different values, on a set of different values of the fractions, the gamma coefficient. So depending on the number of PCA components, the best fraction for this data varies a little bit. So this is an example of integrating Frackridge into scikit-learn API. And that's, I think, the two examples that I will show. There are other examples that you can find in the online documentation and in the code itself.